In 1903, I held in my hands a substance so dangerous that my laboratory notebooks remain stored in lead-lined boxes in Paris to this day, and anyone who wishes to read them must sign a liability waiver and wear protective clothing. More than a century has passed, and the pages remain deadly. That substance was radium, and what it taught me about matter would overturn everything. Physics thought it knew about energy, about atoms, about the very nature of the universe. Most people believe the energy hidden inside matter was discovered through brilliant mathematical theory, through someone thinking very hard and declaring that E equals mc squared. They are wrong. Measurement revealed this truth. Years of labor in a freezing shed. A willingness to believe what seemed impossible simply because the evidence demanded it. You believe you understand matter when you hold a stone in your hand, feel its weight, its solidity, and think you know what it is. Everything is made of atoms. Those fundamental building blocks of the universe, unchangeable, eternal, indivisible, or so we were taught. The very word atom comes from the Greek atomos, meaning that which cannot be cut. And for centuries, this was the foundation upon which all of chemistry and physics rested. Lord Kelvin, perhaps the most celebrated physicist of his age, had declared that physics was essentially complete, that only minor details remained to be worked out. He was profoundly mistaken. What I discovered in a converted shed in Paris would reveal that inside every piece of ordinary matter lies energy so vast, so concentrated, that a handful of certain substances could power a city or destroy one. The story begins in 1896, when the physicist Henri Becquerel made an accidental discovery while investigating phosphorescence, the phenomenon by which certain materials glow after being exposed to light. Uranium salts placed on photographic plates wrapped in black paper were supposed to reveal whether sunlight would cause the uranium to emit rays similar to the X-rays that Wilhelm Röntgen had recently discovered. Paris stayed cloudy for several days, and when Becquerel developed the plates anyway, expecting nothing, he found they had been exposed. Uranium was emitting rays without any external source of energy, needing no light, needing nothing at all, and the rays came continuously, spontaneously, from the uranium itself. This fact alone should have shaken the foundations of physics, because here was a substance emitting energy continuously without any apparent source. Every principle of science at that time said this should be impossible. Conservation of energy, the law stating that energy cannot be created or destroyed, was considered as absolute as any law in nature, and the very idea of perpetual motion had been dismissed as fantasy. Uranium kept emitting energy day after day, week after week, with no visible diminishment, and that raised the question that would consume my life. Where was this energy coming from? This question became the subject of my doctoral thesis at the Sorbonne, at a time when very few women conducted scientific research, and fewer still were taken seriously. Warsaw had been my home, and I had fled the Russian occupation of Poland that forbade women from attending university, arriving in Paris as a young woman with barely enough money to survive. My husband, Pierre, joined me in this investigation, though the original hypothesis was mine alone, and he recognized something in my reasoning that compelled him to abandon his own research on crystals and devote himself entirely to the mystery I had identified. An electrometer that Pierre and his brother Jacques had developed for studying piezoelectricity allowed me to measure the intensity of the rays emitted by various substances with extraordinary precision. My method was simple in principle but demanding in execution, because the rays ionized the air around them, making it conduct electricity, and by measuring this ionization I could quantify the radioactivity of any substance. This was the tool that would unlock the mystery. Every element I could obtain went through testing, and most showed no activity whatsoever. Uranium showed strong activity, and thorium, I discovered, showed activity as well. My reasoning became critical when I found that the activity of uranium compounds depended only on the quantity of uranium present, regardless of its chemical state. Whether the uranium was combined with oxygen or chlorine or any other element, the radiation remained the same, which meant the radiation was not a property of the molecule and was not produced by chemical interactions. Something deeper was at work. The radiation came from the atom itself. Radioactivity became the term I coined to describe this property, an atomic property fundamental to certain elements built into the very structure of their atoms. My contribution, my hypothesis, was that the emission of rays was not the outcome of some interaction between molecules, but must arise from the atom itself, and I published these findings in the Comte's Rendus of the French Academy of Sciences. What seems obvious now was not obvious then, because it meant that atoms, though supposedly indivisible and eternal units, were doing something. They were active. They were changing. And that's when the mystery deepened. Many uranium ores went through my testing. Minerals containing uranium in combination with other elements, including pitchblende, a black heavy mineral from the mines of Jakimov in Bohemia, from which uranium was extracted. Measuring the radioactivity of pitchblende produced an astonishing result. It was more radioactive than pure uranium. This should have been impossible, because if radioactivity came from uranium atoms, and pitchblende contained less uranium per gram than pure uranium metal, then pitchblende should have been less radioactive. 4 times more active is what I measured, and there was only one logical conclusion. Pitchblende must contain another substance, an unknown element, far more radioactive than uranium itself. Pierre and I began the search, obtaining large quantities of pitchblende residue from the Bohemian mines and starting the laborious process of chemical separation. Our workspace was a converted shed that had formerly been a medical school dissecting room, poorly ventilated, lacking even a proper floor, freezing in winter and suffocating in summer, with a roof that leaked. We had no funding, no proper equipment, no assistance, and the work was physical and exhausting. My hands became cracked and sore from handling chemicals as we processed tons of material, repeating the same chemical separations hundreds of times, guided always by the electrometer, following the trail of radioactivity like hunters tracking invisible prey. July of 1898 brought our announcement of a new element, which I named polonium after Poland, my occupied homeland, in the hope that the world might remember that my country still existed. But this was not the end, because there was more radioactivity still unaccounted for. December of that year brought another announcement, made together with our colleague Gustave Beaumont, the existence of radium. Millions of times more active than uranium, that was radium's radioactivity. A tiny amount of radium chloride would glow spontaneously in the dark with an ethereal blue light, and I kept a vial of it by my bedside because it was beautiful. I did not know it was killing me. 4 more years of work produced enough pure radium to determine its atomic weight. Several tons of pitchblende residue yielded approximately 1/10 of a gram of radium chloride, and this tiny quantity was enough. An atomic weight of 226 established radium beyond doubt as a new element, and the unit of radioactivity would later bear my name, the Curie, defined as the activity of 1 gram of radium. This work made me the first woman to receive a Nobel Prize, sharing the 1903 prize in physics with Pierre and Henri Becquerel. And 8 years later, I would receive a second Nobel Prize, this time in chemistry, for isolating pure radium metal. The only person to have won Nobel Prizes in 2 different sciences remains me, and my daughter Irene would later win her own Nobel Prize for discovering artificial radioactivity. She, too, would die from radiation exposure. The price of knowledge can be very high, but the central mystery remained. Where was all this energy coming from? Pierre and our colleague Albert Laborde conducted an experiment in 1903 that revealed the magnitude of what we were dealing with. Using a Bunsen calorimeter, an instrument that measures heat with extraordinary precision. 1 gram of radium emits approximately 100 calories of heat per hour, they determined. Every hour, continuously, without stopping, without diminishing in any measurable way over the course of our observations. 1 gram of radium, a speck of matter you could barely see, radiates enough heat to raise the temperature of an equal mass of water by 1 degree every minute, and it does this hour after hour, day after day, year after year. Heat was not the only emission, because the rays carried energy too. Alpha particles ejected at tremendous velocities, beta particles moving at nearly the speed of light, gamma rays penetrating through lead and stone. The question of the energy's origin consumed us. Testing at every temperature followed. Pierre worked with James Dewar at the Royal Institution in London, using liquid hydrogen to cool radium to temperatures approaching absolute zero, and the heat emission continued unchanged. Heating radium changed nothing. Sealing it in containers, burying it in lead, altering it chemically, none of these stopped the emission or even slowed it. The energy emitted by 1 gram of radium in 1 hour exceeded the energy of any known chemical reaction involving the same mass, and this continued for years. Thousands of times greater than any chemical reaction could account for was the total energy emitted, eventually millions of times greater. Conservation of energy seemed to be contradicted. Some scientists suggested that radium must be absorbing energy from some unknown source, perhaps rays coming from space that passed through everything except radioactive atoms. Careful consideration of this possibility led me to write that such an explanation merely evades the problem. because any exception to the law of conservation of energy can be evaded by invoking an unknown energy source. But this is no explanation at all, unless we can identify that source and its mechanism. The hypothesis remains entirely arbitrary, which left an alternative that was almost unthinkable. The energy must be coming from inside the atom itself. Ernest Rutherford and Frederick Soddy took this reasoning further, showing that radioactive decay involved the transformation of one element into another. Radium did not merely emit energy, but transformed itself, atom by atom, into something else, into radon gas, and then into polonium, and then into lead. What the alchemists spent centuries pursuing, the transmutation of elements, we had achieved, and we discovered it was useless for making gold, but invaluable for understanding the universe. The irony was not lost on us. What this work revealed speaks to the very nature of scientific investigation. In our laboratory, we developed what I came to call the chemistry of the imponderable, working with substances so minute, so vanishingly small, that no balance could weigh them. We could not see them or smell them, and we could detect them only through their radioactive properties. The electrometer allowed us to identify the presence of a radioactive substance, dissolve it, precipitate it from solution, deposit it electrolytically, all without ever having enough material to place on a scale. The electrometer became our eyes, and radioactivity became our measure of quantity. Chemistry without weight is what we were doing, guided only by the invisible rays that our instruments could detect, but our senses could not. This was not merely a technical achievement, but a philosophical revolution, because we were learning that the atom, far from being simple and indivisible, was complex, dynamic, and filled with activity invisible to ordinary senses. Pierre demonstrated, using magnetic fields, that the rays radioactive substances emit are not all alike, because some rays were deflected as if they carried positive charge, others were deflected the opposite way, indicating negative charge, and some were not deflected at all. Alpha, beta, and gamma rays became the names for these three types. Alpha rays were particles carrying positive charge, with a mass approximately 4 times that of hydrogen, and they were in fact the nuclei of helium atoms, ejected from the decaying atom at tremendous speeds. Beta rays were electrons, negatively charged particles far lighter than any atom, accelerated to velocities approaching that of light. Gamma rays were electromagnetic radiation, similar to light but of far higher energy, penetrating through matter that would stop all other rays. Energy resided in each of these emissions. Alpha particles, massive and fast, could travel only a short distance before being stopped, depositing all their energy in a small volume. And this is what caused the burns we observed when radium was held too close to the skin. Pierre deliberately exposed his arm to radium for 10 hours to document its effects, and a lesion appeared that took months to heal. This was how we worked in those days, experimenting on ourselves. Beta particles traveled farther, but carried less energy per particle, while gamma rays could pass through walls, through lead, through everything but the densest materials. These same particles that burned our hands now save lives every day. Beta emitters in medical PET scanners reveal cancers invisible to any other technique, and gamma rays in radiotherapy destroy tumors while sparing healthy tissue. What harmed us has become our medicine. The duality of this discovery, its capacity for both healing and destruction, was something I thought about often in my later years. Mass itself was the source of the energy. Each atom of radium that decayed lost a tiny amount of mass, and this mass was converted into energy. Einstein would later express the relationship between mass and energy with mathematical precision as E equals mc squared, and what he described was being demonstrated before our eyes in the laboratory. We measured it, quantified it, and watched it radiate from our samples hour after hour, burning our skin, fogging our photographs, glowing in the darkness of our laboratory. Every atom contains energy, not chemical energy, which is merely the rearrangement of electrons between atoms, but something deeper, something tied to the fundamental structure of matter itself and locked within the nucleus. The energy in a single atomic nucleus exceeds the energy of chemical bonds by millions of times. A kilogram of uranium, if all its atoms could be made to release their nuclear energy, contains more energy than all the coal ever burned in human history. 25 years without refueling is how long a single nuclear submarine can operate today. The energy I measured with a calorimeter now powers navies and light cities, and in its most terrible application it destroyed Hiroshima and Nagasaki. The energy was always there, waiting to be found. The way this discovery was made deserves understanding. Sitting in an armchair and thinking profound thoughts did not produce it. Measuring produced it. Careful, patient, methodical measurement, trusting the evidence even when it seemed impossible. The electrometer does not lie, and the calorimeter does not lie. When measurements tell you something extraordinary, you must have the courage to accept what they say. Science requires a peculiar combination of qualities that seem almost contradictory. Faith that nature is comprehensible, that patterns exist to be discovered, that patient investigation will be rewarded. All of this is necessary. Doubt is equally necessary, constant doubt, skepticism of one's own conclusions, willingness to be proved wrong. The scientist must believe that truth can be found and must never believe it has been finally found. Our work on radioactivity led us wrong many times, through false leads and errors in measurement. Hundreds of crystallizations were required to isolate radium, each one slightly purifying the material, each one a test of patience and precision. Despair visited me often, making me wonder whether we would ever succeed, but the work continued because the phenomenon demanded to be understood. Lord Kelvin had calculated that the sun could not have been burning for more than 20 million years, based on the assumption that its energy came from gravitational contraction, while geologists protested that the Earth must be far older based on the slow processes they observed in rocks. Radioactivity resolved this conflict because the sun burns by nuclear processes, releasing atomic energy on scales that could maintain its fire for billions of years. The stars themselves are powered by the energy hidden in matter. Pierre used to say that radium could be used to determine the age of the Earth, and he was right. 4.5 billion years old is what radioactive dating has now established as our planet's age. The energy, I discovered, keeps the Earth's core molten, drives the continents across the surface, and powers the volcanoes that shaped our world. We did not know when we began this work where it would lead. Discovering atomic energy was not our intention, because we set out to understand an interesting phenomenon, the rays emitted by uranium, and we followed the evidence where it led, which was somewhere beyond our imagination. Regret is something some have asked me about. Whether the knowledge that atoms contain such energy, knowledge that would eventually lead to weapons capable of destroying cities, should have remained hidden. Science does not work that way. The phenomenon existed whether we studied it or not, and uranium emitted its rays for billions of years before Becquerel noticed them. The energy was always there, hidden in matter, and our task was not to decide whether this knowledge should exist. Our task was to understand what was true. What is true is this: the matter around you, the stone, the water, the air, your own body, all of it contains energy beyond imagining. Not the energy of burning or chemical reaction, but energy locked into the very structure of atoms, energy that manifests only when those atoms transform. Every second, within your body, atoms of potassium 40 and carbon 14 decay, emitting radiation, releasing tiny amounts of that hidden energy. You are radioactive, and everything is. The world looks different with this understanding. Matter is not inert or passive, but contains within itself the capacity for transformation, for the release of energy on scales that dwarf all human activity. This energy was always there, and we simply did not know how to see it. Radioactivity revealed that our perception of the world is radically incomplete. As I wrote many years ago, we are forced to recognize how limited is our direct perception of the world which surrounds us, and how numerous and varied may be the phenomena which we pass without a suspicion of their existence until the day when a fortunate hazard reveals them. The rays existed before we had instruments to detect them, and the energy existed before we had the means to measure it. Nature does not adjust itself to the limits of human senses. Science offers us not certainty, but the gradual extension of our perception. The electrometer allowed us to sense what our bodies could not, and the calorimeter made visible what we could not feel. Through instruments, through measurement, through patient investigation, we extend our reach into the invisible world, and sometimes when we reach far enough, we find something that changes everything. Philosophy did not discover the energy hidden in matter, and first principles did not deduce it. Careful observation of glowing samples in a cold Parisian shed revealed it, along with the persistent separation of tons of ore in search of grams of new substance and the willingness to follow the evidence wherever it led, even when it led to conclusions that seemed to overturn the foundations of physics. This is what the discovery really means. Not a formula, not a theory, but an observable fact about the nature of matter that changes everything we thought we knew. Every atom around you is a reservoir of energy, and most of it lies dormant, stable, unchanging over human timescales. But it is there. Certain atoms in certain configurations allow that energy to leak out continuously, transforming matter, releasing power, demonstrating that the solid world we think we know is filled with hidden fire. We live in a universe far stranger than our ancestors imagined. where matter itself is energy in another form. The stone in your hand is not merely solid, but a compressed storm of forces, holding itself together by bonds we can barely comprehend, containing within its atoms energies vast enough to reshape the world. Studying what lies beneath the surface of things is what I spent my life doing. Not the obvious, but the hidden. The universe rewards those who look carefully and measure precisely and trust the evidence over their preconceptions. This knowledge came at a high cost. Pierre was killed in a street accident before he could see how far our work would reach, and I died of aplastic anemia with my bone marrow destroyed by decades of radiation exposure. My notebooks remain lethal, but the knowledge remains too. The energy was always there, hidden inside matter, and it took only the patience to find it.